Hello, everyone. My name is Williams Robert. I am a student at LJMU, pursuing masters in machine learning and artificial intelligence. Today, I will be presenting my final thesis, and the topic of my thesis is evaluating credit scoring models using deep learning techniques in financial institutions. Credit scoring is a crucial process used by financial institutions to evaluate a borrower's credit worthiness. It involves assessing various factors to determine the likelihood that the borrower will repay their debts. Traditional credit scoring models rely on linear algorithms to analyze credit history, debt levels, and payment behavior. These models are well established and widely used, but they have limitations, especially they may struggle to grasp the intricate nonlinear patterns found in contemporary financial data sets. This can result in less accurate predictions and potentially unfair evaluations for certain individuals. Deep learning, a subset of machine learning, presents an opportunity to enhance credit scoring systems. Unlike linear algorithms, deep learning models can capture complex nonlinear relationships within data. This ability allows for more precise and accurate credit scoring, which can benefit both lender and the borrowers. Uh, this dissertation investigates the efficacy of deep learning techniques in credit scoring models within financial institutions. The primary focus is on evaluating the performance of deep learning models in predicting creditworthiness, comparing them to traditional approaches. The research delves into the impact of feature engineering and data preprocessing on model performance, emphasizing the crucial role these steps play in enhancing predictive capabilities. Additionally, it addresses the interpretability and explainability of deep learning models, ensuring they meet regulatory and ethical standards. Uh, the aim of the study is to investigate how deep learning can enhance the precision and reliability of credit scoring, given the critical nature of credit assessments in financial decision making. Improving these metrics can significantly benefit both institutions and their customers. And to evaluate the strength and limitation of deep learning for credit scoring, while deep learning offers powerful tools for data analysis and prediction, it is important to understand its potential drawbacks like interpretability and explainability, where it may fall short due to its black box nature. Uh, the objective is to evaluate, as mentioned, deep learning efficacy using architectures like MLP, LSTM, and BERT. And the hypothesis is to prove that deep learning models perform better in terms of accuracy and handles complex data patterns when compared to traditional models. And the scope involves uh, assessing deep learning in credit scoring and exploring technical regulatory challenges and recommending integration for enhanced credit risk assessments. Uh, there are few gaps in the research. Before getting into the analysis, we did extensive literature review on credit scoring, and lots of researchers had performed analysis on credit scoring on the available data sets. Despite various researchers, the use of deep learning in financial institutions is still developing. Current research mainly focuses on theoretical aspects rather than practical challenges, regulatory issues, and model interpretability in finance. Financial markets' dynamic nature requires these models to be continually refined. There is a need for comprehensive evaluation that not only assess predictive performance but also addressing uh, practical implementation, regulatory and ethical consideration. This dissertation proposal aims to bridge this gap by evaluating deep learning techniques for credit scoring institutions, focusing on their technical efficacy and practical feasibility with financial institutions. So there are some related works we had explored. Uh, I have noted some of them in the slide. The tools and techniques for the implementation. So to implement our approach, we'll begin with EDA, exploratory data analysis, to gain insights and identify any potential issues in the data set. This step is crucial for understanding the data's underlying patterns and relationships. Following this, we will focus on pre-processing and feature engineering to enhance the model performance. This involves cleaning the data, handling missing values, creating new features that can provide additional predictive power. Once our data is prepared, we will compare different deep learning architectures, including MLPs, multi-layer perceptrons, long short-term memory, LSTMs, and BERT, to evaluate which model performs best. Finally, we will use SHAP to demonstrate model interpretability, ensuring that our results are not only accurate but also understandable and transparent. So I have attached the code that's been used for this implementation. The code contains the import of necessary Python libraries that are required to evaluate grid scoring models using the deep learning techniques. The implementation involves training and testing both MLPs and LSTM models using features derived from text data. The text features were converted into numerical vectors through two approaches: a scratch technique that that generated deep text models without pre-trained resources, and a pre-trained BERT model. The study focused on predicting bank loan defaulters and non-defaulters, leveraging the inherent textual data in bank transactions to improve model performance. The dataset was loaded and displayed using pandas in Python. The dataset was read into a data frame for further analysis and pre-processing. This initial step was crucial as it allows for a preliminary inspection of the data, which includes both text and numeric features. The dataset contains various attributes relevant to loan applications such as employee title, home ownership, annual income, and debt to income. These features represent a mix of categorical and continuous data, essential for building a comprehensive credit scoring model. Text features like employee title and home ownership provide categorical information about the applicants, while numeric features such as annual income and debt to income offer quantitative insights to their financial status. This combination of text and numeric data was pivotal for constructing robust models, and as it enables the capture of both qualitative and quantitative aspects of creditworthiness. The presence of verified and non-verified income statuses further adds layers of complexity to the dataset, necessitating sophisticated pre-processing and feature engineering techniques to harness the full predictive power of the data. Moving on to the next slide. In the initial EDA, we have observed that there is a class imbalance, and from the graph, it was evident that there were more non-defaulters than defaulters in the dataset. This imbalance was a common issue in credit scoring datasets where the number of non-defaulters typically exceeds the number of defaulters. Such class imbalance can affect the performance of predictive models, leading to biased predictions where the model may favor the majority class, which is non-defaulters, over the minority class. Recognizing this imbalance early on allowed for the implementation of strategies such as resampling, class weighting, or anomaly detection techniques to mitigate its impact and improve the model's ability to accurately predict defaulters. The analysis of class distribution was a critical step in the data processing phase, and an imbalanced data set like the one depicted in the graph necessitates careful handling to ensure that the developed model do not become biased. So the implementation step follows as After the pre-processing, we drop some of the irrelevant columns that are not used and converting text features into numerical vector forms. We use two approaches, one with the pre-trained BERT model and another one using a Scratch feature. The text data was extracted, cleaned, and reprocessed to ensure it was in the correct form uh, to be, uh, to be injected into BERT. Once the text data was ready, it is fed into the BERT model, which generates embeddings that represent the text as numeric vectors. These embeddings capture the semantic meaning of text, allowing the subsequent machine learning models to utilize this rich textual information effectively. And once BERT feature conversion is completed, we did the same with Scratch technique. Uh, Text features from dataset converted into numerical vectors. This approach involved encoding text column into numerical values through label encoding. The text data was first extracted, cleaned, and label encoded to transform categorical text data into format suitable for machine learning models. The unique text entry was assigned a numerical value, effectively converting textual information into a numerical vector format. Once the features are converted, we started training a multi-layer perceptron model on both BERT and Scratch features to leverage the strength of different features set similarly. We will train an LSTM model and also we trained the LSTM model on both the BERT and the Scratch features. The accuracy that we had received for training MLP using BERT features is 75%. The ROC curve appears to be like this. It's not that great. However, it appears to be giving up to 75% accuracy. And moving on to the next training where we used Scratch features to train on MLP. And surprisingly, this one gives us 95% accuracy. And the ROC curve appears to be close to 90-degree, which is great. And the next model that we used is LSTM using BERT features. This also appears to close to same as the MLP model, around 78 percentage, and the ROC curve also appears to be similar. And the last model that we had trained is the LSTM using Scratch features. This is performing better than the BERT features, but comparatively, the Scratch features on MLP was giving 95%, which is the best model in our training. So here I have added the performance graph for all the models that we had trained, and it is evident that MLP with Scratch features perform the best. And it is also to note that the custom converted vectors using Scratch performs better than the pre-trained BERT model. Also, we have analyzed the feature importance using SHAP. So it appears that total credit limit, number of mortgage accounts, home ownership, debt to income, some of these features are, provides significant importance to this model outcome. So as a conclusion, after training the models, the result indicates that the models trained using Scratch vectors consistently outperform those trained using BERT vectors across all metrics. Specifically, the Scratch vectors led to a significant increase in the performance with an accuracy of 95.6% compared to the BERT vectors, which is around 75.8. The precision recall and F1 score also saw substantial improvements. For the LSTM model, while both models saw improved performance with Scratch vectors, the LSTM model trained on Scratch vectors achieved an accuracy of 89%, which is better than the BERT vectors. So in conclusion, we can assume that MLP with the Scratch vectors performs better. Given these results, the recommendation is to use the MLP model with Scratch vectors. This combination not only yields the highest accuracy, but also demonstrates superior precision recall and FN score compared to all other combinations. Uh, so for the higher performance metrics, the MLP model with scratch vectors achieve the highest scores across all evaluated metrics. And the performance gains with scratch vectors are consistent across both MLP and LST models, suggesting the scratch vectorization technique is more efficient for credit scoring within financial institutions. So this brings to me the end of my thesis final presentation. I would like to thank my thesis supervisor, Sashi Prakash Tripathi, for the support and guidance. And thank you for your time.